All right, let's dive into a massive question in the AI world today. How do we actually build better AI agents? Now, we're not just talking about simple chatbots here. We're talking about systems that can plan, reason, and get things done. And for a while now, the go-to advice for making them better has been, well, a little too simple. You've probably heard this, right? This idea that if you have a complex problem, you just throw more AI agents at it. You get a specialist for this, a specialist for that, and you build this big team of AIs. It makes a certain kind of sense, you know? The idea that performance just gets better and better the more agents you add to the mix.
But what if that's just a rule of thumb, a piece of folklore that could actually be leading us in the completely wrong direction? Well, today, we're going to move past the guesswork. We're going to dig into the real science of how to scale these systems, and it's all based on one of the most incredible experiments ever done on this topic.
To get some real, hard answers, researchers over at Google decided to put this whole theory to the ultimate test. We're talking about a massive, super-controlled experiment designed to figure out once and for all when, and more importantly, why having multiple agents actually works. And when I say massive, I really mean it. They tested 180 different agent setups, and they didn't just use one model. They ran this across the three biggest players in the game, OpenAI's GPT, Google's Gemini, and Anthropic's Claude. So this wasn't some casual weekend project. This was a seriously deep, systematic investigation.
Okay, so first things first. They had to define what they were even testing for. An agentic task isn't your simple question and answer stuff. No, it's something that needs back and forth, that needs to gather info over time, and crucially, it has to be able to change its plan based on new information. Think about doing a complex financial analysis, not just asking, what's the capital of France?
Now this is where it gets really cool. This table shows the different team structures they put to the test. You've got your lone wolf, the single agent. Then you have independent agents who all work alone and just pool the results at the very end. But then you get into the more complex teams. A centralized model with a boss or an orchestrator, a decentralized one where the agents actually debate each other, and a hybrid that mixes both. As you can see, each one has a totally different level of communication and coordination.
So you've got all these setups, all these complex tasks. What did they actually find? Well, this is where that simple more is better idea starts to completely unravel. The results were, frankly, shocking, and it all boils down to the type of problem you're trying to solve. And this slide right here is the absolute key to understanding everything. Some tasks are parallel. You can break them into little pieces and have different agents work on them all at the same time. Like one analyst looks at revenue, another looks at costs, a third looks at market trends. Easy. But other tasks are sequential. You have to do step A before you can even think about step B. You can't frost the cake before you've baked it, right?
And here it is, the first half of the big reveal. For those tasks you can split up, the parallel ones, having a team of agents was a home run. I mean, the right setup boosted performance by over 80% compared to a single agent. In this case, more is better wasn't just true, it was spectacularly true.
But, and this is one of the biggest buts you'll ever see, for those step-by-step sequential tasks, it was a complete catastrophe. Throwing more agents at the problem didn't just not help, it actively tanked performance, dragging it down by as much as 70%. All the back-and-forth communication and fractured thinking created this cognitive tax that just crippled the whole system. So, the takeaway here is absolutely crucial. There is no single best way to build an AI team. It's not about more agents, it's about the right structure for the right job. The system's design has to be aligned with the task at hand. But performance isn't the only thing that matters, is it? Because in the real world, we don't just need AI to be fast. We need it to be reliable. We need it to be safe. I mean, an error in a medical diagnosis tool or a financial model could be a disaster. And it turns out the way you structure your agents is one of the most powerful safety features you have. The researchers came up with this really important metric they called error amplification. Basically, it measures how a tiny mistake from just one agent can snowball and cascade through the whole system, leading to a final answer that's wildly off base. And just look at this difference. It is staggering. In a system where agents just work on their own and never check in with each other, a single error got amplified more than 17 times. But in a centralized system, with that boss agent, the amplification was cut down to just over 4 times. So why such a huge difference? It's all about that central orchestrator. That boss acts as a quality control checkpoint. It's a bottleneck, but it's a good bottleneck, a validation bottleneck.
It catches the mistakes from the worker agents before they can poison the entire well. For building AI we can actually trust, this is a really big deal.
Okay, so we know now that the architecture has to match the task for both performance and for safety. But how do you pick the right one without, running your own giant experiment every single time? Well, this is where the research takes its most important step, moving from just observing what happens to actually predicting it. They took all of this incredible data and used it to build a predictive model. It's a tool that can actually look at the characteristics of a brand new task and tell a developer, hey, for this job, you're going to want to use this specific agent architecture. This is a total game changer.
And the crazy part? It works. It works unbelievably well. The model was able to predict the best performing structure for a task with 87% accuracy. This is how we move from folklore and guesswork to a real science of AI system design.
And this isn't magic. The model looks at real measurable things, like can the task be broken down into smaller pieces, its decomposability, how many different tools or APIs does it need to use, and how rigid is that step-by-step order. By quantifying these things, developers can now make smart, data-driven decisions right from the start, instead of just taking a shot in the dark.
And all of this leaves us with one final, really fascinating question to chew on. As our base AI models get more and more powerful, this research suggests that raw intelligence just isn't the whole story. The really big breakthroughs might not come from just building smarter models, but from building much smarter systems around them. The future of AI, it seems, isn't just about more intelligence, it's about better design. Thanks for tuning in.